binding of wood, metal, stone, rope to create something. And then eventually it becomes abstracted and becomes emblematic of a culture. And that's the completion of the applied arts, whether it's furniture or architecture. Yeah.
Yeah.
So that's really at the crux of what we do, i.e. just take a few steps back and find out how these things are made and make a decision, an intelligent decision, or the materials you use to make this thing. Yeah.
Yeah. Oh,
Okay.
that's good. Okay.
Is that enough for an introduction, do you think? Then I can skip straight onto the buildings after that. Yeah.
No, we're gonna open up now the Schwarzbrotreihe. Yeah, and
I know what Schwarzbrot means, but
Schwarz
why using it? Why are you using it?
So Schwarzbrot is like a black bread. So
Yeah.
you have to chew a long time.
I see.
And
Okay.
so it's like
Worthy.
yeah, we usually we have we talk about architects talk about their buildings and go from this biggest to the biggest scope to the smallest detail and how long they had to chew on this building
I
and
see.
this
I
topic.
see.
And so and
Okay.
at the end, when we were live, the gift was always a bread. So we gifted the presenter always a bread. Oh, yeah. So
have you not sent like a DHL package to arrive just in time?
maybe we will, let's see. We did it last year. We did some flour. We sent some flour to everybody per package.
God.
So
Make it myself.
Yes, baking yourself.
Okay.
So just for the schedule, I send it to you, but Ingo will introduce you first, and then you hold the presentation, and afterwards there's a small question round, and then you can still be in the meeting. Do not leave. Then we can end everything. Yes.
Yeah, that's fine. Yeah.
Perfect.
I will. I'll stay.
And I think we will start at in like 2 minutes.
Okay. Are you guys still got some sort of restrictions over here? You know, they're going to release everything.
Okay, hello, welcome to our last Schwarzbrotreihe we have for this semester with the topic building without concrete. And today we have building with stone. And live from London, we have Armin, and he's from the office Groupwork Architects. And Armin was born in Berlin and has been settled in the UK since 1974. He began then the independent studio in 2003. and incorporated Groupwork as an employee ownership trust, of which he currently sits as the chairman, as well running the design and detailing of projects. And also Armin was taught, written and lectured on architecture, sat on the RIBA National and International Awards jury, and aids property-related research groups. And today he will talk about his buildings with stone. Maybe you saw it on the poster and the post on Instagram, the facade of the Clerkenwell Close 15, which has a facade made out of stone. And the Groupworks was also part of a study on building a structurally with stone. Yeah, and we are happy that you're here. And after your presentation, there will be like a 15 minutes question round. Please use the YouTube chat or use the YouTube chat to write questions. And yeah, we're happy to welcome you live from Stuttgart. And
Thank you.
You can start.
Okay. Hello, everyone. I'm going to quickly explain why we do what we do. I'll try and keep it brief so we can go straight onto some buildings and how we got onto stone. So the title is Etymology of Architecture, which effectively just means the origins of all architecture. This is not something new to us. It's a question that every generation of architects do ask. And one of the first in the Renaissance period would have been Giorgio Vasari, who you're looking at, who was painter, architect, and sculptor. He was also author of, if you like, the first book on art and architectural history, the lives of the most excellent artists, sculptors, and architects. And being one of them, he included himself amongst them. But what differentiates him from later art historians is that he's interested in what he calls the manner, the idiosyncratic manner of each of the people he's looking at. So he hence gives the life story of each of those, how they became apprenticed to a particular master, a particular skill set, and developed that over their lifetime and became most excellent at it, as it were. And he, even in his day, he debated and argued with his contemporaries the difference between manner and style. His contemporaries wanted to define style as a sort of taxonomy covering a whole period or even a region. So they would differentiate Florence from Venice, for instance. And he would argue that this actually reduces painting, sculpture, and architecture away from the idiosyncratic or the mastery of a particular artist or architect. His book remained on bookshelves, really, as the #1 book on art history until 200 years later with Johann Winkelmann, who published the history of art and architecture of the ancient world in German. It's a bestseller because he's the first person. This is the Enlightenment period, so he's less anecdotal than Vasari. He's actually mapping. He becomes a proto-archaeologist, as it were, as well as art historian. So he properly maps what he's digging up, as it were, reconstructs these, and puts in a timeline sequence: Egyptian, Mesopotamian, Greek, Roman, etc. The past, the ancient past. But he's not an architect or sculptor or painter. So his initial book, his first book, is well received, becomes a bestseller, replaces Vasari on the bookshelves of academic institutions as well as personal libraries. He follows that up with his opinions on the works of the ancients, and in his opinion, Greek is best of all because he conflates the short period of Greek democracy with its architecture, with its sculpture and its architecture. Now, obviously, he's not to know at the time that actually what he's digging up and seeing is bleached white marble, but he effectively says, if we build like the Greeks, we'll be as great as the Greeks, we'll be free of we'll be a republic, we'll be able to self-determine as individuals. And similar as democratic say, will be as great as the past, as it were, and we must build like them in our architecture of unadorned, unpainted, as it were, no polychrome. It must be pure white stone, as well as the sculptures themselves. And obviously, that taste has remained with us to this day. Within a couple of generations, we have Carl Friedrich Schinkel, who's celebrated in Europe as the best of this new neoclassical period, who journeys in England, Scotland and Wales during the Industrial Revolution, initially just to look at the British Museum because he wants to build the Altes Museum. He's commissioned to do the Altes Museum in Berlin. So he wants to see what the British Museum's doing and what its contents are as well. But he's also then on a journey of discovery through the Industrial Revolution of England, Scotland and Wales. And during that period, he comes across all these new structures that are going up, not in the neoclassical style. They're built out of necessity from brick, stone, timber, wrought iron, cast iron, all stitched together. He returns in some sort of crisis back to Berlin. What is this architecture? Is it architecture or not? And he asks Karl Böttger on the left-hand side here to help him discover this, an answer to this question. Böttger with others, so it's not just in Germany, actually, it's in France as well, the École Polytechnique, decide that actually the origins of all architecture, the etymology of all architecture, is in what Böttger defines as tectonic. The tectonic is how architecture is put together. The pieces that make architecture, whether it's stone or timber columns with beams, how they're fixed together. All these elements are the tectonics of architecture. One of Böttger's students is Gottfried Semper, or rather he picks up the theory, is Gottfried Semper. And interestingly enough, he's exiled in London for a while, and is actually at the British Museum, spending his time at the British Museum, looking at the new exhibits that are coming in. And while he's there, he sees these representations of the friezes, Assyrian friezes that come into the British Museum. And in the stone friezes are representations of the throne and the stools of the monarchies, of Assyrian monarchies. And he has the insight, as well as tectonics, how things are made, the architecture and even the applied arts are made. It occurs to him that the reason these motifs eventually exist, what we call ornamentation, decoration, that we don't understand, that Schinkel and others hadn't understood the origins of, he decides is what he terms as the binding, joining and completion of architecture. So the binding and joining is the tectonics, how you put things together. The completion is eventually when you settle culturally or as a community on how you make those things efficiently. Maybe they become decorative, abstracted and decorative and emblematic of a particular culture. So that's the completion of an architecture, as it were. A number of people in Europe are looking at that, and eventually Goury in France, top left, Semper, top right, Owen Jones and Ruskin are also looking at that in the UK. And some of the first people to try and express that without reverting to the Gothic revival. So a lot of Northern European countries immediately reverted to the Gothic revival because they said, okay, this neoclassical architecture is actually pagan. It's not tectonic, while the Gothic is tectonic and representative of our Christian past, as it were. Others, this is later on, Otto Wagner and others are in the sort of secessionist of the Beaux-Arts and classical, and they represent this with the joining and binding, as it were, as an over-expression of these bolts that hold the cladding to the post bank together, and effectively the use of those bolts becomes decorative. So some of those bolts, or most of those bolts, don't serve any real functional purpose, but they become decoration. So it's this idea of binding, joining and completing. So people are searching what is the new language that is emblematic of the industrial or new modern age, in quotation marks. And this carries on all the way through to, as we know, the Bauhaus, that eventually becomes very emblematic of what we understand as the modern period even today, modernism. Interestingly, at the same time in Spain, and there on the top left, is a literature professor who's teaching Dali, Buñuel, and Lorca in Madrid. And we forget that Spain is made up of, well, people tend to forget. He's teaching the idea that there is no modernity, there is a post-modernity. This is in the early 1920s, 1921. Actually, especially in literature and the arts, he's saying we should all be looking as diverse and be as plural as possible, seeking inspiration from this is obviously specifically Spain, the pre-Phoenician, the Phoenician, the Roman, the Arabic, the Celtic influences that still exist in the country, north, south, east, and west of Spain. So he's specifically asking for people to be more plural. Now, obviously, we know where Lorca and Dali and Buñuel went with that. But it wasn't picked up. The idea of this plurality wasn't picked up again for another 50 odd years. And even Jenks changed. At one point, the new radicalism was saying exactly that. We should be living in a plural world. It's playing on, or it's developing the idea of the post-modernity, but eventually we all understand, especially in architecture, we revert back to this sort of Winkelmann method of style. That style is a visual image of the architecture, that as opposed to the tectonic method, which is closer to the Vasari, i.e. the skill set that an architect and artist might develop because they're taught as a stonemason how to quarry the stone, how to carve it, as well as in timber, and that 10,000 hours of apprenticeship eventually develops into innovation and a particular idiosyncratic language for that sculptor or architect. Yet, to this day, we still understand architecture by image, by style, as it were, in the Winkelmann sense, with ever-changing ones. More recently, we have people like Edward R. Jones actually questioning that. Now, what he's not questioning are the sort of ethics behind it, which I'll come on to later, but he does question the idea of details. Are these details, do they make any sense? So I won't labor on this particular point, but if you have the opportunity, I would get hold of his book. Right, let's go into stone. So our first foray into stone is a small house. Small house. It's not even a new house, it's a conversion. But what we found when we were there were elements of the original house which were made of travertine and brass and cherry, and a staircase that had been destroyed and rebuilt, and we wanted to reinstate it, but in the original stone, yet not copy what might have been there in the past, but let's say rebuild it. Now, there's a type of staircase you all must have seen in older buildings, which is stone, and it just goes down, spirals itself down the stairwell. It doesn't seem to have any steel or concrete in it. It's just stone, seemingly cantilevered out the wall. It's not actually cantilevered. It's actually one stone resting on the other, taking its force all the way down and keyed into the wall to stop it twisting. That method was lost in this country, at least, until the 1980s. So I'd read about it when I was a student, and so we were keen to see whether we could do this without any other materials, without steel or concrete. But no English stonemason could do it. So when we were asking who could help us, the English stonemason said, well, the French ones are still trained to build like this in France. I'll If you want to know, I can explain later why that is. But in any case, they're still trained to cut stone and build these type of staircases, and also build buildings. While in England, stonemasons are just used for decoration, ornamentation, decoration, restoration of buildings. So these French stonemasons helped us rebuild or recreate this particular type of staircase. The only what we might have added to that process was making a three-dimensional model and realizing that we could send that model to their cutting machinery, which meant that actually they didn't lose 50% of the stone, because often you lose 50% of the stone while you're cutting out each tread. We worked out a method of using the same stone, larger block, cutting it in half, as it were, but with a twisting drill method that would then allow the other stone to be used on another flight. But otherwise, it's there's just lessons we learned from methods that existed, that have existed for, dare I say, thousands of years. So that's it being erected on temporary timber props and just gently keyed in the wall to stop it twisting out. While we were there, we saw these large blocks come into the workshop. And if you turn that block through 90 degrees, it becomes a column or is a beam. And we were scratching our heads wondering, well, why is nobody using real stone as opposed to all these buildings that are cut with veneers and then stuck on as cladding? And the French stonemasons were then giving us a lesson in I think this is actually in Austria, in stone cutting. So stereotomy, that word earlier, is just simply the projection of cutting methodology, projection of your drawing, as it were, onto the stone and then cutting the stone. And we can see here, this is not contemporary. This is hundreds of years ago. You can't, even back then, they were getting quite complex of their drawings onto the stone. So even with our new software, we were thinking, well, we're advancing this, but actually people are already quite complex with it. If you look very carefully from top left, this is a method of holding up, well, cantilever, what looks like a cantilever, but it's a sort of inverted cone helping to hold up the structure above. And you can see the complexities there going on that top middle drawing of staircases and vaults all marrying up together to transfer load. It's quite incredible, isn't it? Without any contemporary CAD software, as it were. And then top right, that is actually a French engineer in the late 17th century who suggested what's called a reciprocal structure. So each of those stone pieces is cut almost like a brick, but interlocking, and it can therefore transfer its load across a flat soffit to the side. So you don't need huge stone beams that potentially have cracks in them, but actually small briquettes, as it were. And then within a short period of time, within 100 years, that bottom right is somebody building that. So that still exists in France today. And of course, this is how we build today. If we want to put up a stone building, we have either concrete or steel frame. If it's steel, you have to fireproof it, waterproof it, then put your insulation and vapor barrier, puncture through all that with clamps, seal the punctures, and then those clamps have to then be bonded to a piece of stone veneer, which all seems quite a lot of hard work. Is it more efficient? Is it cheaper? Is it better does it have a lower embodied carbon? These are questions we asked when we had our first project, which is on Clerkenwell Close. Clerkenwell Close is outside the city walls. It's medieval. It's and its origins, having been first built on by the invading Normans, and has a long history of radicalism because it's outside the city walls, and printing used to go on there, pamphleteering. So just like your early printing was radical, same here, specifically this area. became the center of publishing. Eventually, William Morris ran the 20th Century Press there. Karl Marx wrote for the 20th Century Press. Lenin actually used its printing presses to do his Russian language paper. And this site is basically next to ours. We're neighboring buildings. And that radicalism pretty much stayed from the Middle Ages until the mid-20th century, by which time confidence in architectural, well, the population of this area decreased by about 50%, but also architecture in general, its radicalism had left us. We'd become a bit more conservative, and nowadays Clerkenwell is typified by sort of the very those stone veneer type buildings, brick and stone veneer buildings that you saw earlier. Our first attempt was to more allude to the half timber structures, and we used a bit of AI software, self-learning software, where we plugged in the amount of metal for a steel frame building, the amount of metal in conventional curtain walling, and asked whether it could reduce the metal involved, and it reduced it by about 30% by making it into an exoskeleton, thin steel plate that was then given a fireproofing, turn it into an exoskeleton. If you look carefully, it's slightly modulated, undulating in its form, because each one of those is deeper or shallower depending on the load path of the stress of the structure. It went down very well with the planning, but one particular conservation officer didn't like it. He said, please use stone. We were scratching our heads thinking, well, we've got no prejudices against other materials. And we wanted to use stone, but our quantity surveyor, the cost consultant, said, well, it must be really expensive. That's possibly why no one's ever used it for 100 years. The structural engineer told us, well, he'd never been educated. No structural engineer is educated in using stone in this country. And we only understood it as this veneer. So again, we returned to those French stonemasons who said this is absurd. In France we used to call it austerity construction because it used to be cheaper than steel or concrete. Why don't you come visit us in France, visit some quarries? So we initially went to some English quarries where they said we've stopped cutting dimension stone, that is stone for structure, about 3 generations ago. We don't have the skills, we don't have the tools, and we couldn't tell you how strong. Couldn't give you a certificate for the strength of the stone either. Go to France, follow the limestone bed under the channel. Remember, stone has no nationality. It all started off, this limestone bed started off at 90 degrees at the equator, and over many millions of years, hundreds of millions of years, has shifted. And it's just in the last few hundred years, it's got an identity, as it were. So off we went to France, and we found these quarries can now cut out stone very inexpensively because they all use industrial diamonds in their saws and only need 1 or 2 people in the quarry as opposed to an army of men hammering away all day to get 1 block out. And occasionally, if a block splits badly, you're still using the old traditional tools. And we found actually there's three types of finish that come out, minimal finishes that come out if you're still using those methods, which are from right to left, saw cutting, a sedimentary finish, a split, or drill split. And then occasionally you'll see a quartz pocket or an old fossil pop out too. This is us testing how the stone might work with a metal boss that supports the floor plate at the back of it. And there you can see our structure going up on temporary propping before the stone comes in to support the floor plates, and then the propping disappears. So you can see there at ground level we have 2 neighbors we're using for support, but then we start with this exoskeleton on 2 sides until we get 2 floors above, and the exoskeleton wraps all the way around. There's our detail. So on the right hand side you can see that's the exoskeleton sitting there with a metal boss grouted into the back of it. So it's all gravity. There's no pins or anything holding it together. And then the metal boss is tied into the floor plate with a nylon bar, a nylon plate that creates the thermal break between outside and inside. That's it in context. So for us, in terms of contextualism, our context was all this 1970s stuff that was pretending to look old. And for us, it was the idea of being architectonic, using materials as structure. So the structure engineering is integrated into the architecture and actually expresses the architecture. That is our purpose, as opposed to, in effect, ignoring the 1970s context, as it were, of trying to fake it. There you see the 3 types of finish that come out the quarry. So again, the principle there is that there's no wastage. You just literally pull it out the quarry and express it as the frame. You'll see there some stones are bigger than others, and that's again using exactly the same software as we used before, telling us that one stone, because of the load path, one stone has to be bigger than smaller. And if you look carefully on the edges, the very edges, there's almost no load, so the stones get very thin there. There are various symbols in there that remind us of the archaeology beneath our feet on that site. Here are interiors. So the interiors are what you call loose fit. So there's no internal structure, which basically means that loose fit means you can do anything you like with it. There might be some apartments, there's offices as well, but in the future you might take all that out because it doesn't affect the structure at all. You can turn it into an office, a hotel, back into apartments, smaller or larger apartments, etc. And on the top you have what's called a blue and green roof combination to avoid pumping water up and down or putting the rainfall into the sewage system. We've taken that lesson to a building that's now twice the height on Finchley Road. And there we had a moment where we realized after this structure, Clerkenwell, went up, we could have made all the floor plates in cross-laminated timber. So here, the plan is that they're all cross-laminated timber, and the exoskeleton there, instead of limestone, is basalt, because basalt performs better in a fire on taller buildings, where the fire performance has to be 2 hours instead of 1 hour. And the basalt can be about half the size, volume of limestone, perform better in that way, which basically means less extraction, less transport, less time on site. So again, lowering the amount of not just the cost, but obviously the embodied carbon. It then occurred to us, well, if we can build 10 stories, can we build any taller? So we asked 2 developers, Central London developers, Canary Wharf and Derwent, for a brief program. Give us the ideal office building that you're looking at, how many floors, how big are those floors, and we tested that, and we found just like a Clerkenwell, that if you look on the scenario, start on the right hand side. Scenario 4 is a concrete frame building and core and stone cladding. You can see there the embodied carbon is what we all expect. And similarly, next one along from the right, if it's a steel frame building, the embodied carbon of steel is obviously a lot more than concrete. On the far left is if it's all stone, so an exoskeleton stone and stone floor plates. So these stone floor plates would be pre-tensioned slabs made of stone. And I'll show you in a minute a slide of one of those that we've experimented with. But then we realized, well, supposing you apply the same idea as Finchley, which is timber, floor plates, and parts of the interior. Well, the timber is carbon sequestrating. What we've already found out is from the far left is that stone, using stone as an exoskeleton instead of a steel frame and cladding it, is 10% or less of the embodied carbon of a steel frame. Yeah, so that's a revelation to us. We thought we might be saving about 20%. We're saving 90%. And that's because stone has no embodied carbon. It's sitting there. It was made for us 250 million, 600 million, whatever it is, years ago. Maybe it came out of the volcano 10 years ago. there is no embodied carbon involved in it. The carbon is involved is in the energy you spend cutting it, transporting it, erecting it on site. So in France, they've already realized this and said, well, supposing, and they've asked all quarries, please slowly transfer to renewable energy. So you're not using diesel equipment on site anymore. Your cutting equipment is all for electric and from renewable sources. To lower the embodied carbon, so effectively your stone arrives on site with 0 embodied carbon, and then hopefully the craneage and other lifting equipment is also from renewable sources, in which case there is no embodied carbon at all. So that's already a big bonus for stone. Now, instead of using stone on the interior, perhaps you can use timber, and we know that timber is carbon sequestrating. Some of you probably already know that 1 ton of timber, depends on the density of timber, if it's balsa wood or wengi or something, highly dense. But on average, 1 ton of timber will hold, when I say hold, will be responsible for having sequestered 1.6 tons of carbon dioxide, which sounds odd, doesn't it? How can 1 ton of timber weigh 1.6 tons of carbon dioxide? Well, I know some of you will be ahead already. You will know that the timber, sorry, the leaf, as it were, on the timber is taking in the carbon dioxide, and through photosynthesis, it's actually pulling it apart. So the carbon dioxide goes into the leaf, it destroys the molecule, and releases the C and the O2. It releases the O2. So 1.6 tons of carbon dioxide is actually the carbon dioxide that comes in. The O2 is released, so the weight of the O2 is released, as it were. The carbon is taken into the timber and makes it cellulose. It's part of its structure, as it were. So what it's doing is not actually holding the carbon dioxide in, it's actually just breaking it up, releasing the oxygen and holding the carbon alone. So the carbon dioxide no longer exists, as it were. So it's carbon sequestrating timber. So supposing you hypothetically make everything out of timber, well, it basically means that overnight we've created a carbon sequestrating construction industry. The narrative is then build more and you absorb more atmospheric carbon. But obviously we can't build everything out of timber, especially larger structures or structures that need particular fireproofing. And in this country, where since Grenfell, we're very conscious of that. The building regulations have changed. They may change again, but that's another debate. So our superstructure tends to be stone now. Well, we're arguing it should be stone. So if you mix that, and you can see there in scenario 2, you mix the amount of timber with the stones. The stone is the exoskeleton, and everything internally is timber, the floor plates. You've actually ended up with a carbon negative building. Slightly controversial to say, because at the moment the way we calculate whether something is carbon negative or not is to say, even if you use timber, because we do not know what's going to happen to it in the future, it's like the family holding money in the bank, but we don't trust the offspring to not spend it and gamble it away. So we will not bank that sequestered carbon, because we assume it will be demolished and the timber will either be burnt for fuel or sent to landfill and the carbon dioxide released while it's decomposing. Made, as it were, while it's decomposing. So what do? You material passport your timber, and that way you remain carbon negative, and that's the key to all of you as you go forward in your careers, really. What we also found was a timber and stone version of that tower is cheaper. Not a lot cheaper. It's about 10% cheaper, but most developers like Canary Wharf and Derwent, 10% in the construction cost is significant enough. I'm almost done, but I'll give you examples of people who have built in stone in the past and currently. So where are we? Perrodin, Poulon, and Perret. So this is Perrodin in France. who is already building low rise as well as mid rise, and then he won a competition, I think in Switzerland, for a taller building, all again in stone. This is Poulon, who in the 1950s was building all in stone, because at that time France, this is what they call austerity construction, because it was cheaper to build in stone than it was in steel or concrete. And if you look carefully, the stone is the way he worked it out was if you cut stone so it's manhandleable, you know, it can be picked up, dropped into place, as opposed to all of it having to have expensive cranes at the time. It should be cheaper than steel or concrete, which it was. So he persistently won his tenders in France. Top right is a building on the docks by Poulon. Again, it's not this what we would look at and say it looks like a classical style. It's got an arch. The proportions are such. Well, the proportions are such because they follow the most efficient way of cutting the stone. If you look on the bottom left, that's unité. Now, in that period, everybody was very keen to be modern, and obviously, you know, Corbusier, the steel and concrete was emblematic of the modern. It was the style of the modern, as it were. Now, Corbusier couldn't build everything. Not everybody knew that style. Not everybody had the skills to create that sort of formwork. And of course, that building ended up roughly about 10 times what Poulon was spending on the docks in Marseille for the same apartment sizes. So super expensive. And of course, we know that what happened then throughout the rest of the world is everyone's effectively trying to copy, recreate the sort of unité type buildings, but at a budget, and those budget obviously undermined the integrity of the structure as well as its appearance, as it were, and has given modernism a bad name, I would argue. So if you remember our 17th century French engineer, somebody, as a pair of architects, old A&U architecture in Palestine, actually, who've created this flat arch, this 17th century flat arch, sorry, flat soffit of reciprocal stones, reciprocally loaded stones, only a couple of years ago. This is French stonemasons using exactly the same reciprocally loaded small pieces of stone, but what they've done is taken the software from and said, from a flat soffit, let's bend it, create a dome, and that software obviously very easily translates into cutting of those stones and then locking them in together, grouting them together. Of course, today our software can do anything. I mean, in terms of its shapes, the shapes we can create, and and even the cutting tools can follow pretty much what the software is telling it to do. So again, there's minimal wastage, and arguably, you know, some buildings deserve more attention and energy spent on them than others, but there is no limit today really to it. This is us experimenting with Italian stonemasons who are undertaking research there of what to do with a lot of waste stone. So some waste stone, it just sits in the quarry in a pile looking for a purpose. This is taking it and bonding it with a sort of basalt cement. And if you look on the top left, you can see there's 3 layers to it. This is one of the first experiments we undertook. And they just initially wanted to experiment with a flat piece to use as a cladding panel. And we said, well, actually, if it's starting off as small broken pieces that you're then bonding, you could just rest them on a piece of formwork, and that formwork follows the structural path that then comes self-supporting. So this is our experiment to create to bond it and then create these 8 meter long truncated arches. Our experiments go on. So there's a house we've been working on where it's simply just stacking stones. As you find them in the quarry, reduce the amount of energy and cutting you need, stack them up and see how tall you can make that. On the left-hand side, you can see there's I can't remember how long that is, maybe 15 meters. So you've seen precast concrete planks that then quickly sit on a frame to create the floor plate, on top of which you have to put a concrete screed to fill in all the gaps and create a level surface. Here we're experimenting with effectively the equivalent of a precast concrete plank, but a post-tension stone plank, which, because it's cut, needs no concrete on top. No, it's already level. And you combine the cost saving of doing that, plus the fact that it's nice stone to look at, so you don't need any suspended ceilings or other things to hide the crinkly tin or precast concrete plank, then that ends up being cheaper than doing the other method, the concrete method or the crinkly tin method with pouring concrete on top. There are some other experiments of lintels and other post-tensioned soffits, and then even reducing the amount of time on site by grouting at the back of some of those stones, bonding them together with this grout, basalt grout, so you can transport them and lift them into place. So then that grout is not structural, it's there just to keep it together while you're transporting, lifting it into place. The stone is structural of its own, as it were, in its own dimensions. Oops. Yeah, that's us again experimenting with more of that waste stone. I think that might be our conclusion. Yes. That's the end.
Wow, thank you.
You're welcome.
It was such a beautiful presentation. I really loved everything about it. The start, the aesthetic of the buildings, the aesthetic of the stones, of the different haptics, with the different methods to cut the stone, and then also the further research outlook in it. Yeah, so everybody at home, feel free to use the chat to give us some questions. And maybe I have also a few questions. You said before the presentation, maybe you tell us why the French are trained to build like this later. Why are the French building like or still trained to build like this?
They like a lot of countries, they've got a lot of historic towns, which were, I don't want to say abandoned, but the population began to diminish because people are going into the larger towns for work. Yeah. And they went into disrepair, and they had a central government initiative to maintain them, keep the historic fabric, and also create jobs. So what they said is that each of these historic towns needs to be maintained, its fabric maintained, but it needs a stonemason who's part of the maintenance regime. So each town needs a stonemason, qualified stonemason or two. So one, the training has to occur. So you're maintaining that training, and they're trained exactly as they've been for hundreds of years. And then you're creating jobs, you're retraining, and then making demand for the material itself. So I guess, I don't know, what do you call that? Vertical economic integration, as it were.
So I think so at least here at our university or in my whole studies, I've never learned really building with massive stone. But why do you think is that so? Why did we lose this know-how? Maybe also the trust in building with stone. And do you think concrete plays a big role in this?
Yeah. I mean, the one thing that people don't, I mean, this is all going to sound very conspiratorial. But one thing people forget is that there's actually a gardener come potter, landscape architect in France, who invented reinforced concrete. He was inventing it for giant pots. Put mesh inside the cement, and it becomes a stronger and bigger pot, as opposed to ceramic, terracotta pot. And then he realized, it's quite strong. I can make this in parts, and I can make garden gazebos, structures. I can make garden bridges. I can prefabricate elements in reinforced concrete. But he's a gardener, landscape architect. He's not a very good businessman, and very quickly, all his patents were bought by Germans. Germans and Swiss. Yeah. And he ended up in penury. He ended up with no money. The French government couldn't believe he'd made no money, so they prosecuted him for hiding his wealth. And eventually, he was ruined. He had literally penniless. And in the end, they realized he had no money, and they gave him a pension, which is as a job as a tobacconist for the rest of his life. Yeah. While the people who had the patents realized the potential, and those are German, Swiss, some French, and but the market wasn't there yet. They said there was potential, especially for big industrial buildings, big infrastructure projects. In architecture, people are still in the classical mindset. We build, and it has to be all decorated, ornamented. There's lots of ornamentation, but Auguste Perret is innovating in it, isn't he? Yeah. So he's a French architect who's innovating in it. Fernand Poulon works for Auguste Perret. So does Corbusier. Because he's the cutting edge of this new material, this reinforced concrete. But Fernand Poulon recognizes that it has its limitations. It's very expensive. You're using lots of timber, formwork, and then lots of metal, lots of expertise, because the market isn't there yet. The production isn't there yet. All this, the craftsman skills aren't there yet. It's not ubiquitous as a material. It's very expensive. So he says it has its place for big infrastructure or warehouses where nobody cares too much about the quality of finishes. But day-to-day building for housing should remain in stone. However, Corbusier, one of his childhood friends, is studied science while Corbusier went off to do arts and eventually architecture, and becomes a lobbyist come promoter for industry. And he pays Corbusier a salary, says, I will fund your office every year, so a salary for you and your staff, if you do R&D in concrete, reinforced concrete. Yeah, I have a whole industry that's crying out for more architects to use more concrete. So, the domino house and everything else, the flat slab with columns, free plan, all of that comes out of that where Corbusier is trying to do the R&D and express how useful this material is going to be. And he's very good at it, isn't he? And but nobody's really taking much notice until the 1940s, when in our desperation to be suddenly more modern, escape our fathers, as it were, and grandparents, and the modern period is emblematic with this modern architecture, while stone is of the past. So despite the fact it was more expensive, off we go. That's what we're going to do. And then the industry catches up. So now the material is ubiquitous. So just like junk food is ubiquitous, wherever you go, any supermarket shelf you go to, all this stuff that would have cost more in the past. Why do you want to mix sugar and fat in equal measure in every product? Why do you do that? Because it's expensive. Well, not anymore. Yeah? And it stays on the shelf longer, and you pay a little bit more because it's got value add and all the rest of it. A lot of it you don't pay a lot more because it is ubiquitous, but it's not very healthy for you. It's not very good for you. Yeah. So physically, for your for your body, it's not very good for you. So in the same way, concrete, steel, it's high embodied carbon. It's ubiquitous as a material. It's cheap. The skills are all there, while the stone, we've lost the skills of stone masonry and carpentry, as it were. That's got to catch back up, but it's unhealthy for us. Yeah, so it's embodied carbon is unhealthy for us. That's the sort of analogy of it. Has that answered your question?
Yeah, it's more than enough. It's
All right.
yeah, no.
All right.
So I have further question with
Yeah.
how can you be sure of the statical properties of a stone that you're using? So
Yeah.
because you showed already in the pictures there might be some holes in it or some cracks in it. So
Yeah.
what can you
Yeah.
be sure, and how much do you have to over dimension it actually?
Yeah. No, absolutely. Okay, so I mean, essentially, depending where you are on the quarry, you take a sample of that stone, you send it to testing. And there's what's called 2-point load tests, 3-point load tests, 4-point load tests. And this is all to do with, normally it's used for cladding because there's wind load. And the wind load is not just pressure against the cladding, but it's also sucking the cladding out. So there's a multiple load test on a piece of stone, pressure on it to see at what point it fails. Now, quarries that cut stone out on a regular basis, they're industrialized, they're already doing, to be able to sell their stone, they're already saying from this part of the quarry, from that part of the quarry, from that part of the quarry, these are the structural properties of the stone. What do you want it for? Do you want it for a kitchen worktop? Do you want it for a floor tile? Or do you want it for masonry superstructure? Yeah. Oh, then go to this part of the quarry, not that part of the quarry. Go so many meters deep and not this deep or that deep. Yeah. So that's very easy. If you're looking for the, your engineer will tell you it needs to be of a certain structural strength. Very quickly on a database, you can find the quarries that are supplying that structural strength, and then you reduce the spectrum of quarries to the color of stone you want, the type of stone you want. Yeah, and slowly but surely, you might go and visit 3 or 4 quarries for the final appearance or something else. Yeah, cost. What's cheaper.
How early do you bring the stone quarry into the design process? Is that like
that is I mean, hopefully that's answered the person's question on the structural, how you guess the structure, or how you find the structural quality of the stone. In terms of sizing it, our engineer, because he hadn't built with stone before, said, I'm going to pretend it's unreinforced concrete. In other words, it's got the same structural properties of unreinforced concrete. If it splits, it breaks. So I will therefore size it. An unreinforced concrete, I can't remember exactly what it is. It's something like 20% bigger or more of reinforced concrete. Yeah. And reinforced concrete is already 20%, 30% bigger than a piece of steel, et cetera, because, as long as the steel's come out of a mill at a certain quality, we know its failure rate will be quite small. Yeah. How early do we involve quarries and stonemasons? Out of habit, we involve all specialists now very, very early. So, and this is not just because we want to know the type of stone, what it looks like, whether it can cope, but also the cost of it. Yeah, because what you guys will learn when you go out into industry is, we're in a habit as architects of having all the control taken from us. Now we're just left to make lovely drawings, and then somebody else does the costing, somebody else does the structural engineering and all the rest of it. And then every time the cost consultant says we're ready, we're now ready to go out to tender to the industry and find out whether this is on budget, because I think it is on budget. I don't know how many buildings you've been involved with, but I can guarantee you there's no building that comes in on budget. Yeah, they all come in over budget, and everyone's scratching their head. Oh my God, what have we done? How do we save this building and save our client? Well, in this country, we call it value engineering. Yeah, they call it value engineering. And of course, the quantity surveyor, the cost consultant, doesn't go to the structural engineer and say, I need to reduce the cost of this building by 15% to bring it back on budget. Can you take 15% of your columns away? Yeah. And he doesn't go to the mechanical electrical engineer and say, can you take 15% of your water supply or heating or something, yeah, air conditioning away? He always goes back to the architect and says, your architecture, your lovely drawings, can you take all these lovely fiddly bits or change the material, yeah? You see what I mean? The architecture is reduced to an application, a sort of wallpaper. So, which is returning to the argument that architecture should be integral to the structure, the binding, joining, completion, the tectonics. Yeah, because then the quantity surveyor can't say, "Can you please take this architecture away?" Because the building will fall down. Yeah. So to ensure that we're on budget, we go to all these different consultants, specialist subcontractors, whether it's stonemasonry, metalwork, glazing, the foundations, the green and blue roof, and say from the outset, look, this is what we're thinking. are we thinking in the right directions? Is there a better way of putting this together? And often, on every project, we've started the process, an iterative process. It has to go through cycles. They'll turn around to us and say, well, why have you done that? Well, I don't know. Is that not logical? No. You can reduce the amount of materials you've done here. Why have you got this piece there and that piece? Oh, don't you need it? No. Take it away. And suddenly, slowly and slowly, the building is reduced to its principal elements, and the architecture can still flourish from that. Yeah.
Yeah. So when we talk now about the global warming potential of building with stone, it all comes down to the cutting, of course, but also the transport. And the transport has like the biggest impact on it, as far as I understood it. So how is like the supply or the density of stone quarries in, for example, Great Britain? So
terrible. That's why we had to go to France. We went to a stone quarry in England, and they said we cut floor tiles and kitchen worktops, tiles, but no idea how to cut dimension stone for structure. We don't have the tools, we don't have the skills. Just go across the channel. If we'd got it from England, we would have saved ourselves 5% of the embodied carbon. We already saved 90. We would have saved ourselves another 5%. So half the embodied carbon of that stone was transportation, and it was only from Lyon, so it's not coming from China. That's just coming from Lyon. Yeah. Now, for the time being, in the larger scheme of things, saving 90% is pretty good, isn't it, compared to a piece of steel? But yes, if we manage to tool up, as it were, the British quarry industry, stone industry, then we save another 5%. If we make it all, cut it, transport it, and erect it on site with renewable energy, then we're, I don't want to say saving 100% is zero, because obviously you still have to make that equipment that cuts it, transports it, erects it, and it has to be renewed and maintained, and that's still burning, energy and no doubt has some embodied carbon. But you can see where it's heading, slowly but surely. Faster, I would argue, than the cement and steel industry turning to zero carbon. Yeah.
Yeah. And how do you think about stone as an ending resource, because it's not regrowing? Is there enough stone on this earth to supply enough buildings?
Yeah. Okay. Well, I don't know. Does anybody else want to answer that question? Whoever answered that question, I'm hoping they're holding a glass of whiskey ready to. If we cut a section through the planet, what is it? What is that? What is that section? What does it look like?
It's a huge section, I would say.
Yeah, I know, but can you remember when you were a child what it looked like? In the core, is iron, molten iron. Yeah, and then from there on, what's that? That magma, molten stone. Yeah, all the way. I mean, really, where the planet is a giant globe of molten stone and iron, and just because it's touching cold space, the perimeter of it, the edge of it has cooled. Yeah, and that's what we're all walking on this cooled edge. If we had a finger and it could push through the cooled edge, a volcano of erupting magma would come out. So we're never gonna use all that stone. Just think of it like us, like ants or termites walking on this stone and taking one piece and putting it up there to make a tower or a house or something. We're just moving some of it here to there. We're never going to run out of it. Yeah? Whether it's volcanic magma or sedimentary over 600 million years, that we're never going to run out of it. There's a very good example, if anybody's interested in it. If you look at Edinburgh, look at a map of Edinburgh, you'll see old medieval Edinburgh and the castle and all its medieval structures, the new town of Edinburgh, which is 17th, 18th century, and 19th century Edinburgh, all made from the same stone, all came out the same quarry. And if you Google I can't remember what it's called now. It's basically a shopping, one of these retail parks where you park your car. There's a food supermarket, a supermarket for pet goods, another one, yeah, all around the car park. That is the quarry that supplied the whole of Edinburgh. It is now just a small car park. Yeah.
Crazy. Yeah.
Yeah. So we'll be fine. There's plenty of stone.
So, yeah, I think we're coming now to an end to the presentation, and it seems like really stone could be also a material for the future. I think it was also part of the exhibition, The New Stone Age. I really like the name of it. So, like, going to the roots, looking when we didn't have enough energy, how did we build, and how should we build in the future again?
Yeah. I mean, remember, we're not trying to eliminate all steel or concrete. We're just trying to say, if you step back and think about it intelligently, do you actually need that steel and concrete? You know, you're not in a seismic zone where you need lots and lots of bracing and superstructure. You're not building a giant tunnel or a long span bridge. A lot of the housing and other structures can be built of timber and stone. Yeah, a mixture of those two. And still remain, if you what we call over here material passporting. Yeah, so that basically means that the materials of that building are identified, so the day it comes to demolition, they're reused. They're not thrown into a landfill, and if it's timber, it's just then decomposing and making more carbon dioxide, or if you're burning it, again making more carbon dioxide. If you passport that timber, you've actually got a carbon negative building that is genuinely carbon negative, mixture of stone and timber, and reusable in the future if it's demolished in 100 years or whatever time. So it's about stepping back, making an intelligent choice about the materials you use. You're bound to use some metal, yeah, and some concrete. But it's just reducing the amount. And before you know it, you've got a construction industry, instead of being a contributor of, 38 odd percent of atmospheric carbon, you've got a sequestration industry. If we all did it overnight, yeah, you may ask, where the hell's all that timber coming from?
Yes.
There's a Professor Tom Crowther at ETH Zurich, whose paper in 2019 said there's 1.7 billion hectares of land that we have cleared in the past. Deforestation for shipbuilding, for houses, for farmland that we no longer use. It's in private and public ownership. If we planted all that over the next decades with natural indigenous woodland, within 100 years, we would be at pre-industrial age at levels of atmospheric carbon. Yeah. Now, these are just papers at the moment, but that's sort of knowledge in our hand. Knowing that some of that, and I think we did a study here where we worked out it's about 12% of that 1.7 billion hectares could go on a cycle of cutting, regrowing to supply a building industry. That's a thought experiment that overnight you'd say, well, if everybody clicked their fingers and overnight we had that wood and we specified that, we would be a carbon sequestrating industry. Yeah. So obviously, it's keep that in mind, and that's for us to push forward, specify, make our clients go in that direction. And if we all did it within no time at all, we'd be at too much, not enough carbon dioxide, too much oxygen. Do you know what happened then during the last period when we had too much oxygen? Mass extinction of a certain type of species, and then insects and animals grew very big because they had too much oxygen for their muscles. Shall I leave you on that note?
Well, let's hope not for big insects.
All right.
Then,
all right.
Everybody at home, I wish you a wonderful evening, and I hope you also had a good semester. And this was now the last lecture in the topic Bauen ohne Beton. Maybe there might be a next semester motto happening in the winter semester. Let's see. Yeah.
Wo ist mein Schwarzbrot?
Oh, yeah, Schwarzbrot.
It's coming by DHL.
Yes, maybe.
All right.
So like a Schwarzbrot, okay. Yeah, you asked before what is a Schwarzbrot, and the Schwarzbrot is like, it's a certain type of flour. that makes it very dark, but also very nutritious. And so that's,
I look forward to it. Okay.
Okay.
Auf Wiedersehen.
Bye.
I can work out how to say Auf Wiedersehen. Bye then. Bye.
Okay. Bye. Thank you so much. It was
You're
a
welcome.
wonderful presentation. And
You're welcome.